Hello students, the next part of the syllabus is solution of the Lagrange's linear PDE of the type PP plus QQ equal to R. So here PP plus QQ equal to R is one of the standard partial differential equation called Lagrange's linear PDE, where P, Q, R are the functions of x, y, z. And remember that here x and y are the independent variables, z is a function of x and y. Okay, and already you know the notations that this is small p, the small p is a dou z by dou x, and the small q is a dou z by dou y. Okay, now for this Lagrange's linear PDE, so linear PDE means the degree of this equation is 1. Okay, the degree of this equation is 1. Now the general solution of this linear PDE is given by pi of uv equal to 0. So this pi of uv represents the general solution, means we are going to find the values of u and v. Okay, so where this pi is the arbitrary function and u is a function of xyz, then v is also the function of xyz, and so this u equal to c1 and v equal to c2 represents the solution of the given PDE. Okay, now our work is to find the values of u and v. Okay, now so here this dx by p equal to dy by q equal to dz by r. So this is called the auxiliary equation of the PDE PP plus QQ equal to R. Okay, when the given PDE is in the standard form, then we write the auxiliary equation as dx by capital P equal to dy by capital Q equal to dz by capital R. So this is called the auxiliary equation. Okay, now we discuss how to find the solution for the PDE PP plus QQ equal to R. The first step is put the given linear PDE of the first order in the standard form PP plus QQ equal to R, because sometimes the given equation will not be in the standard form. So we need to write in the standard form as PP plus QQ equal to R. So when you write in the standard form, it becomes easy to write the auxiliary equation. Means when you write in the standard form, we take the value of P, we take the value of Q, we take the value of R, then we can write the auxiliary equation easily. Okay, the second step is we write the auxiliary equation. When you write in the standard form, then we write the auxiliary equation dx by the value of P equal to dy by the value of Q, then the dz divided by the value of R. So these P, Q, R in terms of x, y, z. Okay, this is the second step. Now the third step is given by solve the equation 2. So equation 2 is what? It is the auxiliary equation. So this auxiliary equation we solve by some well-known methods. So that depends on the auxiliary equation. We apply the procedure. Okay, by solving the auxiliary equation, we obtain u of xyz equal to c1 and v of xyz equal to c2 as its solution. Then we taking these values, we write the general solution in the form of pi of this value of u and this value of v equal to 0. So this gives the general solution of the given standard form PP plus QQ equal to R. Okay, now as here it is written, we have three rules for getting two solutions, u of xyz equal to c1 and v of xyz equal to c2 of the auxiliary equation. Okay, so here three rules, because depending on the auxiliary equation, we have three different rules, because depending on the functions of xyz, that is depending on the pqr, because we cannot apply for any kind of auxiliary equation, we cannot apply only one procedure. Depending on the nature of the pqr, we have different rules. Okay, now in this video we discuss the first rule. That rule is called method of grouping. Now, what is this method of grouping? See, the first step, as in the working procedure we discussed, we write in the standard form, that is pp plus qq equal to r. Then we write the auxiliary equation dx by p equal to dy by q equal to dz by r. Okay, so after writing auxiliary equation, by this rule 1, that is method of grouping, what it says, if dx by p equal to dy by q from these two fractions, means when we write the auxiliary equation, we choose the first two fractions. Okay, it is not necessary that we have to choose always the first two fractions. So for explanation here, I'm saying that take the first two fractions, such that here in what are these p and q? P and q are the functions of x, y, z. Okay, suppose from this, means from this fraction, z variable can be cancelled or it is absent. Okay, I just explain this how it is possible. I take the first two fractions, that is, suppose it contain y and x. Sorry, we can take z and x equal to, then the second fraction is dy, and this also z into y. After choosing the first two fractions, so this is the some possible other fractions. Okay, now from this, as it is explained in the procedure, z may be absent or it may be cancelled. So in this we can cancel z, right? Then we have dx by x, dy by y. So these two we are going to integrate. This is the one possibility, right? The other possibility is, when we choose the first two fractions, dx divided by x equal to dy by y. So in this we do not have z variable, so this is a dx having only function only x, this is dy having only y. So in this z variable is absent. This is a one possibility. The other possibility is containing z and it is possible to cancel. So what we have to maintain, when we have dx and dy, here we must have only functions of x and y, that you remember. That is, if we have only dx and dy, we must have only x and y. Okay, in other way, suppose if there is a dy and dz, then we must have only y and z, or here is suppose this also possible, or dy by z, dz by y. So this also we can solve by taking the cross multiplication, that is y into dy, z into dz, we can integrate. So remember that if we have dx and dy, we must have functions of x and y. If we have y and z, sorry, dy and dz, we must have the variables y and z, not x. Okay, then if we have dx and dz, we must have x and z, not y. Okay, so this is what we are going to maintain, right? This is what the procedure explains, right? So taking the first two fractions where z variable is cancelled, it is possible to cancel, and then or it is absent. Okay, so then as we discussed, we are going to integrate the fractions, we get the first solution u of xy equal to c1. Likewise, we take the other two fractions. hmm, when we take the other two fractions like dy by cube equal to dz by r, so in this we must have only y and z, not x. Okay, remember that. Then this by integrating, we get the second solution. Okay, so as we have only in terms of y and z, we denote v of yz. So in this we have only in terms of x and y, so we denote as u of xy equal to constant. Okay, this is the integration constant. Then using these two, we write the solution as pi of this u and this v equal to 0. Okay, so this is what we call the method of grouping. Okay, now we consider one simple example. Okay, so here is the example: xz into dou z by dou x plus yz into dou z by dou y equal to xy. So it is in the standard form, that is p, right? This is a capital P, dou z by dou x, plus q, that is functions of x, y, z, and this is q, right? xz into p plus yz into q equal to xy. Okay, now it is in the standard form, so we write the auxiliary equation as dx by p, that is xz, equal to dy by q, that is yz, equal to dz by r. Now, so here choosing the fraction, it depends. We can, it is not necessary that always you choose the first two fractions then last two fractions. It is not like that. So you can choose any two fractions such that we can easily separate the variables. Now here by choosing the first two fractions, so z we can cancel, right? So we have dx and dy and having only x and y, right? So this is in the standard form. This on integration, log x equal to log y plus integration constant I take as a log c1. From this we get the value of we can take this okay, log x equal to log y plus log c1 as a log x equal to log y into c1. Cancelling log, we get x equal to c1 into y. Okay, so therefore the value of the constant is c1 equal to x by y. This is the first solution. So similarly, we take the last two fractions. By taking the last two fractions, and here the one the condition here, we have dy and dz, as it is said that we must have only y and z, but in this case y only cancelling, y is cancelling, we are getting in terms of x, but this should not be there. Dy by z, y cancelled, dz by x, but this should be in terms of y, right? So therefore what we do, we are going to replace this x here, x as a c1 into y, we are going to write in terms of y, because as it is said dy dz is there, means we must have only variables y and z. Therefore we are replacing x equal to c1y, we got in terms of y, right? Then these on separating the variables, c1 into y dy equal to z into dz. Okay, so this you can integrate. Integration of y is y square by 2 into constant c1 equal to z square by 2 plus integration constant. Okay, so then taking LCM, c1 y square equal to this z square, or you can cancel 2 on both sides. You can cancel 2 on both sides. Here we get 2c2. Okay, this 2c2 is a constant, so that we can write as a simply c2. Then we are replacing c1 because we want the value of second constant c2, replacing c1 as a x by y. Okay, then 1y cancel, we got x into y minus z square equal to c2. So okay, don't get confused with the 2c2 or simply c2. So this constant is a that constant we can put in a form like c2 only. Okay, so now we have c1 as a x by y one solution, c2 the another solution xy minus z square. So therefore the general solution is given by pi of c1 value x by y, then c2 xy minus z square equal to 0. So this is the solution of the given PDE of the form pp plus QQ equal to R. Okay, thank you.